All right, new section. In 3.5, we're going to learn about trig derivatives. And you might be like, what? Trig derivatives? I already know trig derivatives. You already taught me a couple sections ago that the derivative of sine of x was just equal to cosine of x, and the derivative of cosine of x is equal to negative sine of x. These are trig functions. I know all these. I'm good. Well, yes and no. I mean, these are trig functions, but they're not the only trig functions, right? Depending on how long it's been since you took a trig class, you may or may not remember that there's 6 different trig functions: tangent of x, cosecant of x, secant of x, cotangent of x, in addition to sine and cosine. And while we've talked about these two, we haven't talked about these other 4. The good news is, using what we know about the derivative of sine and cosine and the quotient rule that we learned in the last section, we can come up with the derivatives of any of these 4. Because as you may or may not remember from a trig class, depending on how long ago it was that you took trig, you can rewrite any of these 4 functions in terms of sine and cosine. And since you already know the derivative of sine and cosine, that allows you to figure out the derivative of any of these 4 functions. Not sure what I'm talking about? Let me demonstrate. Suppose you were asked to figure out the tangent of x. Well, what you could do is say tangent of x, isn't that the exact same as sine of x over cosine of x? I'd be like, yup, tangent is the same as sine over cosine. So instead of thinking about it as the derivative of tangent, couldn't I think about it as the derivative of sine over cosine? Yeah, absolutely. And then you're like, the derivative of sine is cosine, and the derivative of cosine is negative sine, so I guess my answer is cosine divided by negative sine. And I'd be like, no, absolutely not. Because when we're taking the derivative of a quotient, you can't just take the derivative of the top and the derivative of the bottom. You have to use the quotient rule. Oh, yeah, right. Okay, so what would be the derivative of sine over cosine? Well, what you do is, using the quotient rule, we take the derivative of the top, the derivative of sine of x, and we multiply that by the bottom, the cosine of x, and from that we want to subtract the derivative of the bottom, the derivative of cosine of x, and multiply that by the top, the sine of x. And then don't forget, you're not done there. The quotient rule also has this denominator, which is the denominator over here, cosine of x squared. We're not done because we still have the d over dx symbol in there, so we got to figure out the derivative of sine. Fortunately, we know the derivative of sine, right? Learned that a couple sections ago. The derivative of sine is just cosine. Hopefully that's something that you've added to your memorization list. So what I have up on the top here is cosine of x from this, and then another cosine of x from this. So cosine of x times cosine of x. And from that I want to subtract the derivative of cosine, which maybe you remember is negative sine. So I'm subtracting a negative, in other words, I'm adding sine of x, times another sine of x for this sine of x. I want to divide that entire thing by the cosine of x squared. We don't have the derivative symbol written anymore, so I guess we're kind of done. Well, yeah, I mean, I guess you are kind of done, but this answer can be simplified significantly. And I think this is an instance where we should do that. Cosine of x times cosine of x is just cosine squared x. That's what this means. Similarly, sine of x times sine of x is just sine squared x. And down in the denominator here, where I have cosine of x squared, that's typically written as cosine squared x. So one way I can simplify this is just by getting rid of parentheses and writing things in kind of prettier forms. But I don't have to stop here either, because you also might remember from a trig class that there's this thing called the Pythagorean identity. And what it says is that for any angle x, sine squared of that angle plus cosine squared of that angle is always equal to 1. If you have that kind of in your back pocket and you look up at the numerator here, you might be like, wait a minute, cosine squared plus sine squared, isn't that the same as sine squared plus cosine squared? Yeah, absolutely. And you told me sine squared plus cosine squared equals 1, right? So instead of writing the entire numerator here, couldn't I just make it 1 over cosine squared x? I'd be like, yeah, that's way simpler, right? The derivative of tangent is 1 over cosine squared x. If you open up a textbook, you'll never see written that the derivative of tangent is 1 over cosine squared x, because 1 divided by cosine is the same as secant. Therefore, 1 divided by cosine squared is the same as secant squared x. The derivative of tangent is secant squared. It's easy to just move on at this point, but that fact is kind of remarkable if you really think about it. First off, it's kind of cool that we can figure this out just using facts we already knew in the quotient rule. It's also kind of cool that it simplifies so nicely. But if you think about tangent and secant squared, those are things that don't appear to have any connection at all, right? If you think about the graph of tangent of x, for example, you may or may not remember that that's a graph that kind of looks, loosely speaking, like this, with these asymptotes. Anytime the denominator, the cosine of x, is equal to 0, so that happens at pi over 2, and again at 3 pi over 2, and 5 pi over 2, and negative pi over 2, and so on. And in between those different asymptotes, you get this kind of S-shaped thing going on that repeats over and over again. If you think about the slope of this graph, there's no reason it should have any connection with the graph of secant of x. I mean, secant is 1 over cosine, so maybe you remember that the way you come up with that graph is you sort of start with the cosine graph, which repeats every 2 pi, so I guess this would be 2 pi here, and this would be pi somewhere around here. But it's not the graph of cosine I'm interested in. I want to know about the graph of secant, and so since secant is the reciprocal of this graph, anytime this graph is equal to 0, the graph of secant will be 1 divided by 0, which is undefined, so I'll end up with vertical asymptotes on this graph as well. And then maybe you remember that the way that you can draw the graph is sort of connecting the dots at the minima and maxima of the cosine function. What I'm saying is a quick sketch of the secant graph are these little parabola looking but not actually parabolic u's that sort of attach to the graph of cosine of x, loosely speaking. This is not the graph that I want, right? I want secant squared. This is just secant. But when I'm squaring something, all the negative becomes positive, and really all that happens is if the height is 1, 1 squared is 1, so it stays the same. And if the height is a number greater than 1, when I square a number greater than 1, it becomes, well, even greater than 1. So it essentially just has the effect of stretching these u's up and flipping any ones that are below the axis above the axis. What I'm saying is a quick graph of secant squared x is, I don't know, kind of sort of this thing that we see in purple here. Far from perfect, but good enough. The fact that the height of this graph in purple tells you the slope of this graph in purple is kind of wild. I mean, maybe it doesn't blow your mind too much because everything in trig feels like it's kind of related through these different identities. But I think it's kind of cool that the information that really defines this function, how steep it is at any given point, is perfectly given by some other trig function that until now didn't really seem at all related to this trig function, and we have to square that trig function. I don't know. I think that's cool. Maybe you don't. Really, the big takeaway here is just that the derivative of tangent is equal to secant squared. And there's nothing special about tangent. We can do that for any of these 4 trig functions. In fact, in my notes, the next 3 things I do is prove that to you by figuring out the derivative of the next 3 trig functions. I'm not going to do that. Maybe I'll demonstrate one more and leave the last 2 as an exercise for you. So the derivative of cosecant of x. If I remember right, the homework asks you to do this exact same thing. So I don't need to do all 4 for you. But I think if I show you cosecant and you've already seen tangent, you'll have all the techniques necessary to do it on your own. You're trying to figure out the derivative of cosecant. The first thing to do is rewrite cosecant in terms of sines and cosines. Why? Because you know the derivative of sine and cosine. Maybe you remember that cosecant is 1 over sine. So instead of thinking about I have to take the derivative of cosecant, think about I have to take the derivative of 1 over sine. This is a little bit weird, but it's a fraction of something divided by something, so I could use the quotient rule. I'd get the derivative of the top, the derivative of 1, times the bottom, the sine of x, minus the derivative of the bottom, the derivative of sine of x, times the top, which is just equal to 1. And then don't forget, you got to divide by the bottom, sine of x, squared. Nice thing happens here, because I'm taking the derivative of a constant here, it's just equal to 0. And 0 times anything, sine of x in this case, is just 0. So what I get up in the numerator is 0 minus the derivative of sine of x. The derivative of sine is cosine, and cosine times 1 would just be cosine of x, divided by sine squared x. What I'm saying is that the derivative of 1 over sine of x is equal to negative cosine of x divided by sine squared x. And since 1 over sine of x is the same as cosecant, this is the derivative of cosecant. However, much like we saw up here, nobody leaves the answer for the derivative of cosecant in this form, because you can simplify it. How do you simplify it? Well, 0 minus cosine of x is just negative cosine of x. So I have a negative something. That something you might think of as cosine of x divided by sine squared x, but instead of thinking about it as cosine x divided by sine squared x, think about it as cosine of x divided by sine of x times sine of x. In other words, cosine of x divided by sine of x times 1 over sine of x. Talk yourself into the fact that what I have written on this line is identical to what I have written on this line. There's no reason you'd know to switch sine squared x into sine of x times sine of x unless somebody demonstrated it for you, which is why I'm demonstrating it for you, right? Written in this form, maybe it's a little bit easier to see where this is going. I got cosine over sine, and I have 1 over sine. Wait a minute, those things sound familiar. Cosine over sine, isn't that just cotangent? Yep, sure is. And 1 over sine, isn't that just cosecant? Yeah, absolutely. So could I change this into negative cotangent of x times cosecant of x? Sure could. So that's my final answer. Well, okay, this is kind of a weird nitpicky thing, but usually people write this as negative cosecant of x times cotangent of x. No idea why, but this is what you'd see if you looked into like a math book or something. So maybe this is the form that I should leave my final answer in. The point is just the derivative of cosecant is almost just cosecant. You just have to remember to change the sign and tack on a cotangent of x. You can do steps almost identical to this to figure out the derivative of secant. And then you can do steps almost identical to what you see up in purple here to figure out the derivative of cotangent. And what you'll see if you do all that work is the derivative of secant is just secant times tangent, and the derivative of cotangent is negative cosecant squared. You don't need to memorize these immediately, but I think what you'll want to do are add these to your memorization list in time. And if that feels a little bit overwhelming, I really think about it as 3 different groups, right? We already know the derivative of sine of x, that's just cosine of x, and the derivative of cosine of x, that's the negative of sine of x. So sine and cosine are kind of related. The derivative of sine is cosine, the derivative of cosine is almost sine. You just have to remember to tack on this negative sign here. Well, it turns out that tangent and secant are kind of related as well. The derivative of tangent is secant squared. The derivative of secant involves tangent. It would be nice if the derivative of secant were tangent squared. That would make life a lot easier. It's not quite that, but you can kind of see the different pieces. If you already knew that the derivative of tangent was secant squared, then maybe you would have kind of connected in your brain tangent and secant. And when you're taking the derivative of secant, maybe you could remember that, well, for secant, I'm left with the secant and that trig function that's kind of related to secant, the tangent. In my mind, I group up the 2 of these to remember them, and then I group the 2 of these to remember them, and then finally I group the 2 of these to remember them. What you'll see here is, in the same way that the derivative of tangent is secant, the derivative of cotangent is cosecant. I mean, it's almost the exact same. We're just kind of tack on a co to the start of both these words. Oh, and there's the negative sign. Right? Derivative of tangent is secant squared. Derivative of cotangent is almost cosecant squared. Be so cool if it was just cosecant squared. Just like it would be so cool if the derivative of cosine was sine, but it's not. Hey, wait a minute. Cotangent, cosecant, cosine, all of those leave me with a negative derivative. That's kind of cool. Maybe that's something I could take advantage of for my memorization purposes. Yup. Tangent, secant, and sine all leave me with a positive derivative. That's cool. The relationship between tangent and secant is very similar to the relation between cotangent and cosecant. Similarly, the relation between secant and tangent, namely that the derivative of secant is secant times tangent, is almost the same thing we see down here. The derivative of cosecant is cosecant times cotangent. Secant, secant, tangent, cosecant, cosecant, cotangent. Right? They're almost identical, except got to make sure you have the negative sign here because it's one of the co-derivatives. You don't need to memorize any of these 4 new trig derivatives because you could always just come up with them using the quotient rule. But I think what you'll find is it's so much quicker to just kind of have these in your back pocket and not have to rederive them every time. So I'd recommend eventually getting to the point where you know all 6 of these trig functions, just kind of having their derivatives memorized. For what it's worth, these 2 are by far the most common that you see. These are the second most common, and it's fairly uncommon to see these down here. But it is possible, so it's not a bad idea to know them. That might feel a little bit overwhelming, but I have lots of good news for you. The first one is we're getting pretty close to the end of our list. Our list being we want to take the derivative of any function out there, and we're getting pretty damn close. We have almost all of our building blocks and almost all of our major rules. More good news is we're not developing any new rules or any new building blocks in this section. So we're done with new information for this section. All we got to do remaining in this section is some examples just to give you some practice with this stuff. But in the interest of keeping these videos to a reasonable length, I think what I'm going to do is stop this here and do the examples in the next video.